This is the Magnet Motor Lab by Morgan Kiriakosa, Hannah Lufkin, and Emma Dittmar. The problem we were investigating in this lab was how we could create an electric motor from a permanent magnet. Once we solved this problem, we attempted to answer the following question. How does changing the poles of the magnets touching the negative end of the battery affect the direction that the wire spun and the magnetic field being created? Our result? Flipping the magnet's poles changed the direction of the magnetic field and the force while not affecting the magnitude of the magnetic field. In order to understand this lab, it was crucial to make a model. Our prior knowledge of the model was that we knew about forces, so for example, for electrons to feel a magnetic force, they need to be moving. We knew that magnetic field lines go from the north to the south pole. We knew electric field lines go from positive to negative end. We knew the right-hand rule, where your first finger is the current, your thumb is the force, and your middle finger is the magnetic field, all 90 degrees to each other as depicted in the picture. And we knew the magnetic force equation. We made a few assumptions when making the model. First, we assumed that each magnet out of the 7 that we had the same magnitude of strength. Additionally, we assumed that velocity stayed constant after we flipped the magnets, as in both directions had the same exact velocity. Finally, we assumed that the electric field lines and magnetic field lines intersect completely perpendicularly. We think our model is good for many reasons. First, we were confident because once we changed the poles, the expected result occurred. The direction switched. Additionally, it was consistent with the right-hand rule and the force equation because the wire spun in the opposite direction and we changed our right hand and it also went in the opposite direction. Finally, we knew the directions of the electric field lines and magnetic field lines prior, and these were also represented in the model.
In our system schema, we included a wire, magnet, battery, and earth, and they interact through gravitational contact, electric, and magnetic forces. For our force diagram, we looked at the top of the battery where the wire touches. So the wire has a gravitational force pulling down, a normal force pulling up, and the magnetic force is coming out of the page.
In our experimental design, we had 7 magnets, 1 wire, and 1 battery. We attached the unit of magnets to the negative end of the battery and the wire to the positive end of the battery, but the wire had to be touching the magnets in order to complete the circuit. To move the motor, a current was pushed through the wire from the positive end of the battery to the negative end, and the magnetic field was produced from the magnet from the north pole to the south pole of the magnet. A force was also created because of the magnetic field, and then since the wire had moving electrons, the magnetic force was able to act on the wire, pushing it perpendicular to the force in the field. We also collected data when one pole of the magnet was attached to the battery, and then we switched to what pole was attached, and then we observed that the direction that the wire rotated around the battery changed.
The magnetic force equation is given so that the current is denoted by the I, the length of the wire is denoted by the L, and the magnetic field direction is the B. The current is generated by the battery, so current moves from the positive end to the negative end of the battery, and the magnetic field is generated by the magnets, so this moves from the north pole to the south pole. These two fields intersect, assuming that it's at a perpendicular angle, so this generates the force that will push the wire clockwise. When the poles are flipped so that the south pole touches the battery, the force on the wire makes it go counterclockwise.
We used an IO lab to determine the strength of magnetic field coming from a magnet, and for one magnet it was 150 microteslas, so the unit of 7 batteries was 1050 microteslas. So that means that the only thing that was changing when we flipped the battery was the direction of the magnetic field, but not the strength. And the other thing we measured was the rotations per second of the wire when it was moving around the battery and the magnets. And when it was moving counterclockwise, it had 2.08 rotations per second, but when it was moving clockwise, it had 1.5 rotations per second. And the similar rotation speeds indicated that the only thing that was changing is the direction of the magnetic field and the force, but the magnitudes remained the same. One of the errors we had when doing this experiment was that the wire would not stay on the battery when we were recording the revolutions per second, and it was also very hard to count how many revolutions happened per second because the wire was moving so quickly. But our final conclusion was that flipping the poles of the magnet changed the direction of the magnetic field.